In this video, we shall look at Faraday's law. Let's assume you have such a loop, and that is the area vector, A. Now let's assume you have magnetic field penetrating through the loop, as shown by the arrows in blue. The angle between the area vector and the magnetic field vector is theta. Let's assume the magnetic field is increasing with respect to time. So the magnitude of the magnetic field that's penetrating this loop is increasing with respect to time. Faraday's law states in such a case there will be an EMF in that loop in this direction. So that is the direction of EMF. When we say direction of EMF, there is an induced current in that direction. Let's denote it by I. Faraday's law relates the EMF induced to the change in magnetic flux through the loop. And this is how the equation looks like. EMF induced equals minus the rate of change of magnetic flux through the loop, where this magnetic flux through the closed loop is defined to be the dot product of the magnetic field vector and the area vector, like that. So that is Faraday's law. Next, we shall look at the sign convention that determines the direction of the EMF and therefore the direction of the induced current. To do that, we have to assign signs for the EMF. Let's look at this particular case. Since the magnetic field is increasing with respect to time, that means the magnetic flux through that loop must also increase with respect to time, so that d dt magnetic flux is greater than 0. But in the equation that defines the Faraday's law, there is a minus sign in front. So what that means is the EMF in this case is negative. This is how the sign convention works. Let's look at that loop. So that is the area vector. Let's grab this loop with your right hand, pointing your right hand thumb along the area vector, like that. A positive EMF is defined by the direction of this curl. So if the EMF is going like that, that means it's positive EMF. The negative EMF therefore must go in an opposite direction, as represented by the red arrows. So that is negative EMF. Since for this case we have worked out the EMF to be negative, then the direction of that induced EMF is like that, namely like that. And the direction of the induced current will follow the direction of the induced EMF. Now assume for the same diagram the magnetic field is decreasing with respect to time. That means the magnetic flux through the loop will also be negative, namely decrease with respect to time. Now this negative would interact with this negative and give you a positive EMF. So since the EMF now is positive, according to the right-hand rule that we have just discussed, the direction of the induced EMF will go like that, and the direction of the induced current will also go like that. Having understood Faraday's law and the sign convention that goes with it, let's look at the second important point. And this has to do with electric field within that loop. Since there is an induced current that indicates motion of positive charges in that direction. For that to happen, let's assume the charge is Q. There must be an electric field that pushes this charge in that direction, which gives rise to that electric current. As this positive charge moves and make a complete loop, the work done by this electric field on such a charge is given by this expression. It is the work done by this electric force, not electrostatic force, but electric force of some kind. The work done by such a force on that charge is given by this expression. It is QE dot dl. Because we are computing the work done as the charge moves in a complete loop, we have to represent it by such a integral. And this work done can be related to the potential energy given by Q times EMF. After all, EMF is some kind of voltage, so Q, the charge in Coulomb times voltage, is the potential energy of this charge. So the Q goes away, and we can rewrite the above in a following manner. E dl equals EMF, which is minus d dt magnetic flux through that loop. So this is another way to state Faraday's law in terms of induced electric field. And we can also use this expression to calculate what that induced electric field is. Let's look at the following problem. An electromagnet produces a uniform magnetic field of 2 Tesla over a cross-sectional area of 0.3 meters squared. We place a coil having 150 turns. That means it is a coil with many turns, and the number of turns is 150 in this case, and a total resistance of 2 ohms around the electromagnet. The current in that electromagnet is smoothly reduced in the electromagnet until it reaches 0 in 25 milliseconds. What is the current induced in the coil? So what we have is you have a coil with certain number of turns, 150 turns that is, and you have magnetic field going through it, 2 Tesla, and this magnetic field is coming from some kind of an electromagnet that is powered by some electric current. Let's call it I. And after 25 milliseconds, this current goes to 0. That would immediately switch off the magnetic field that's going through the coil from 2 Tesla to 0 Tesla, and this happens in 25 milliseconds. So because you have the change in magnetic field with respect to time, that implies the magnetic flux through that coil will also change with respect to time, which in turn implies induced EMF and therefore an induced current. That is what we want to determine, the induced current in the coil. So first, let's determine the induced EMF in that coil. We don't care about the direction of this induced EMF. Let's just determine its magnitude. Its magnitude is given by d magnetic flux dt, or quite simply the change in magnetic flux over the change in time, or the time interval. Let's not forget that this coil has 150 turns, so let's include that number of turns in front. So the EMF is n 150 turns. The change in magnetic flux is given by the final magnetic flux minus the initial magnetic flux over the time interval 25 milliseconds, 25 times 10 to the power minus 3 in seconds. So that equals 150. The final magnetic flux is 0 because when the current in the electromagnet is switched off, then there is no magnetic field from the electromagnet. So 0 minus the initial magnetic flux is the initial field, which is 2 Tesla, times the cross-sectional area of that loop, which is 0.3 meters squared. In this example, we assume that the direction of the magnetic field and the areal vector A is the same, so angle between them is 0, so cosine 0 is 1, so therefore the initial flux is just 2 times 0.3. And you divide that by the time interval, 25 times 10 to the power minus 3 seconds, and that should give you an EMF of 3600 volts. Note, we are looking only at the magnitude, hence 3600 volts. Since we know the total resistance of that coil to be 25 ohms, you can determine the induced current as quite simply EMF over the total resistance, so 3600 volts over 25 ohms, and that's going to give you an induced current of 144 ampere, and that solves the problem. Problem 2. A magnetic field directed out of the page changes with time according to that expression, where t is in seconds. The field has a circular cross-section of radius 3 centimeters. So this entire circular region with radius 3 centimeter is penetrated by a magnetic field in the direction out of the page or out of the plane as indicated by these dots. What are the magnitude and direction of the electric field at point Q? At 2 centimeters from the center. So point Q is right there. And we want to determine the direction and the magnitude of that electric field at that point at 2 seconds. Obviously, we need to figure out the electric field from the equation that we have just discussed a few minutes ago, namely that equation. So let's just determine the right-hand side of this equation to begin with. So EMF can be determined from Faraday's law, and it's given by d dt magnetic field. Let's first determine the magnitude of the EMF first. So d dt magnetic flux equals d dt B times A. Note that the direction of the magnetic field and the area vector, which is also coming out of the page, is the same. So angle between them is 0 degrees. So B dot A is simply BA. The area is constant, so you can take that A out. D dt B. We are interested in electric field at point Q, which is a distance 2 cm away from the center. So let's trace out a circle with a radius 2 centimeters like that. B is given by that expression, so dB dt, or the derivative of B with respect to time, is quite simply 0.1 t. That's it. That's what you get by differentiating that expression with respect to time. When t is 2 seconds, your dB dt will simply become 0.2 Tesla per second. So you can substitute dB dt with 0.2. Now what about this area? That area is the area shaded here, a circular area with radius little r 2 centimeters. So substituting for the A as pi 0.02, I'm converting cm into meter squared times 0.2. You will get the magnitude of the induced EMF. The induced EMF is 2.51 times 10 to the power minus 4 volts. So there we go. We have the value of the induced EMF at that point, namely 2.51 times 10 to the power minus 4 volts. Now let's determine the direction of that induced EMF. The magnetic field is increasing with respect to time, so the magnetic flux is also increasing with respect to time. That means the EMF has got to be negative. So if the positive EMF going that way, the negative EMF must go that way, according to our sign convention rule. So that is the direction of the EMF, and that is also the direction of the induced current. That means the direction of the electric field at that point is going like that. And we need the left-hand side to determine the magnitude of that electric field. The electric field is constant everywhere in that circle, so you can take that E out of that integral. This integral refers to the circumference of that red circle. So that is just 2 pi times that radius of that little circle, 2 centimeters. Convert that into meter, 0.02 meter. So E times that equals 2.51 times 10 to the power minus 4, which is the induced EMF. And you can solve for the magnitude of the electric field at point Q. And it turns out to be 2 times 10 to the power minus 3 volt per meter. The direction of it at point Q is to the right, with that much magnitude. And that solves the problem. Thank you for watching.